lecture 9 of kinetic theory of gases. In the last class, if you remember, we had talked about the various, we had done the derivations for the various types of speed, like the average speed, the RMS speed, the most probable speed. We are going to look up into another form of the speed when we talk about two molecules approaching each other. We will do the derivation today, and before that what we are going to discuss is what is the parameters what we look into when the two molecules approach each other. Okay. So, when we talk about two molecules approaching each other, we visualize the gas model. It is a random movement of large number of particles. Molecules are moving randomly and they are colliding with each other in a random fashion, and the path of an individual molecule is random not only in 1D, but actually should be visualized in 3D, like not only on the paper which we are which is depicted in this diagram. This is actually extended to 3D, means the 3-dimension x, y, z coordinates, like if you are having a molecule in a cubic container, similar to something like that, and the motion of the molecules are so random and the movement they are undergoing is so random, and based on the whatever assumptions we had for the kinetic theory model is extended to this gas model. So, in the whole process what we are looking into is the behavior of gas molecules in random manner, and this sort of behavior at times are called random walk process. So, when they are all molecules are moving randomly, what we like to know is how is going to be the behavior of the particles when they come into contact with each other, or when they interact. In other words, we say when they collide. So, that is what we are looking into today, is the collisions of the gas molecules. Now, when two gas molecules are approaching each other, then what we should be looking into, what is the mean speed with which they are approaching each other. Whether the mean speed which we had calculated previously is the same or something different is what we are going to look into. But before that, let us look into the Lennard-Jones potential of any two molecules when they are neutral molecules, when they are interacting. What happens? You have seen this potential energy curve in your books. So, what is this potential energy curve arising from? When you have two neutral molecules, they come together or they approach each other, what happens? The nucleus is a positively charged and the electrons are surrounding it. So, there is a repulsion between the two electron cloud when they come closer, or if they are sufficiently apart, then they have a attraction from the electron to the nucleus of the other. So, these sort of interactions between the nucleus and the electron of one with the nucleus and electron of the other molecule is what we are going to look into when we are looking into a Lennard-Jones potential. What does it essentially say? That when two molecules come close to one another, the intermolecular interactions between them produce a potential energy interaction. This is the potential energy which is going to be arising out of the interactions of the electron and the nucleus of one molecule with that of the other. When the two molecules are very close to each other, this is what the distance is. When they are very close to each other, what you see, the potential energy is very high. So, in this potential energy curve, this is a positive side. So, this is a very high positive interaction which we are looking into, and this positive interaction in the molecules are associated with repulsive forces. As since it is a very strong value of the potential energy, we say this is a strong repulsive force existing between the two molecules. Suppose the two molecules are in an intermediate distance from each other. What do you see? The potential energy of interaction is negative, this is the intermediate distance, and this is the potential energy is negative where the value is small. So, we say, and the negative is associated with attraction of the molecule. So, the molecules, two molecules have attraction towards each other, but these are weak attractions. But what happens when the distance is very large, somewhere like this? Then the potential energy is supposed to be approaching 0. So, this is what we are going to look into when we are talking about a gas molecule colliding, and what is the basis on which we are going to derive their collision frequency and other stuff, other parameters. So, the model which we are looking into is known as the hard sphere model, and this hard sphere model assumes certain things. What we have when we have two molecules, see, these are two molecules we are looking into, and two molecules are of the same dimension, or they are similar molecules. They can be dissimilar molecules, and each of them have a certain diameter. This has a diameter d1, this has a diameter d1. Here the diameter is d2, this is the diameter d1. So, what happens when you are talking about a hard sphere model? The intermolecular potential is supposed to be 0 at distance when the centers is between these two, like this is one center, this is another center, when the centers of the two molecules differ by d1 for a similar molecule, or by half d1 by d2 for two molecules which are dissimilar. These are the two diagrams you should understand. This is becoming d1 because both the diameters are equal. So, d1 plus d1 equals to 2 d1, and divided by 2 we are taking the half of the distance. So, it is the distance between the two nucleus or centers of the molecules is d. Similarly, if this is the one, this is the diameter for this is the diameter for this, half of this diameter, half of this diameter, if I add them, and then the distance is actually half of the d1 and the diameter of half of the diameter of second molecule. So, the intermolecular potential is 0 at distances what? When the distance is greater than that of the value half d1 plus d2. Did you understand? So, we are looking into a model something like this. So, this is the potential energy approaching 0. This will happen only when the centers of the two molecules, if the similar molecules is at a distance greater than d1, and if their distance are they are dissimilar molecules, then their distances are half the diameters of the one of the diameters plus another diameter added together and half of that. So, this is for two dissimilar molecules, and this is for the similar molecules. The molecules 1 and 2 do not collide. When will these molecules collide and when will they not? These two molecules do not collide or interact, 1 and 2, or we can consider one type of molecule, similar kind of molecules, unless the distance between their centers is equal to this. So, what we have at greater than this distance, the separation distance between the two nuclei is greater than the values for half of d1 by d2 or d1 for similar molecules, and it is equal, and it will collide and do not collide if the other distances are unless the distances are in the nearest approach distance of the diameters separation of between the two similar molecules, or half the diameters of the separation of the two nuclei of the two dissimilar molecules. So, we are clear now. So, what we have assumed the potential energy to be 0 at a condition where the distances between the two nuclei of the molecules are greater than the value of the half of the diameters of the two molecules, or it will be, and it will collide only if their value is equal to the diameter of the half of the diameters of the two molecules. So, after they collide, what happens? As they are going to follow the kinetic model, after they collide or interact, they bounce back and they behave like a billiard ball, and this is like what you call as an elastic collision. So, now we summarize what we have just now said. If two molecules are alike, they are similar, means diameters are similar, they will collide with each other only if their centers come within a distance equal to d1. d1 is the diameter of 1 plus the diameter of 2 divided by 2. So, the internucleus the difference between the distances of the from one center to the other center of the molecule is the diameter d1, the diameter of one molecule. But if these molecules are dissimilar, they will collide with each other only if their centers come within the distance of half of d1 by d2, d1 plus d2, this is this distance. Okay. So, now when we talk about how they are, what is the distance where they should come in contact, so only then we can consider they have to, they will undergo a collision. Before that, we should also see what is the speed through which they are approaching each other. This is not as simple as it is depicted, or I am going to, as the way I am going to discuss right now, but let us assume what we are, it's a simplistic approach or argument to understand the velocity of approach of the molecules. We call this as the mean relative speed of approach of molecules when one is approaching the other, and this we will see is related to the average or the mean speed which we have calculated before. So, if you have two molecules like you have here, if you have two molecules and they are moving in this, see here this is, it is not visible, they are moving in the say same direction, that means they are going to be keep moving and they will not collide. So, their mean relative velocity can be taken to be 0. So, this arrow, there is an arrow which is going towards this side. Okay. So, the two molecules having the same direction, when they are moving with the relative mean speed of that molecules when they approach each other will be always 0. That means both of them are moving at a particular velocity. So, their approach is not likely, so it is going to be 0. When two molecules are approaching each other head on, like you have here, one directly approaching the other, what do you expect? When the two molecules are approaching each other head on, the mean relative speed should be the relative speed of the two molecules. It should be 2 the mean velocity of approach. So, this I think this needs to be a correction. This should be 2 the average velocity of each of the particles. Okay. Now, when suppose the molecules are approaching from any particular direction, because we know they are randomly distributed and they are moving randomly. So, to find out we use more or less the Pythagoras theorem to find out the mean relative speed or mean relative speed of approach. What we see, this side is approaching with velocity v, this side is also approaching with velocity v. So, what we say, we take the Pythagoras theorem and see the velocity of approach is becoming the relative mean speed of approach becoming under root 2 into the average speed. So, this is the average speed which you are having, this is going to be twice the average speed and this is going to be 0. This is twice the average speed is when they are coming head on. Okay. And the last one what we are going to see, since we have not put any direction or any we have taken a very simplified model, we have not put any angle, because all the molecules are moving in the velocity space and they are all vector quantities, velocities are vector quantities, we are not associating any angle, we are saying they are randomly moving. So, if they are randomly moving, then we have assumed, and this is the most simplistic approach, we have assumed that it is under root 2 into the mean speed which we have calculated previously. This can be this calculation can be taken up a little more detailed if you are understanding what is a vector parameter. To understand the velocity and speed with which molecules approach one another, it is necessary to assess the relative average mean speed of the molecules involved rather than just the average velocities, okay, because they are randomly moving. So, if they are moving in random manner, they are moving at any particular direction. So, we cannot take it to be 0, we cannot take it to be twice the average speed. We just have to find out a term which can be applied or can be related to the average or mean speed, but we call that as a relative mean speed, and this is the speed where these molecules approach one another. So, the relative velocity or relative mean speed which we are going to be looking into is what we are going to now discuss. The relative velocity of two molecules approaching each other can be expressed in terms of their vector velocities. So, this is one vector velocity and this is another. They are random molecular velocities, they are randomly moving from x, y, z any direction. So, what we can see, if we have a say velocity 1 associated with one molecule, another velocity 2 that is associated with the other molecule, and this is, since this is if I am taking this as a positive, I take this as negative. So, this is having a negative velocity, that means it is moving in the opposite direction. So, the relative velocity of approach we can say will be the v1 minus the velocity vector v2. Okay. So, the magnitude of the relative velocity, how do you find out the magnitude of the relative velocity? We have already defined what is the relative velocity. The magnitude of relative velocity can be expressed as the square root of the scalar product of the vector itself. So, what is the vector? Vector is this one. So, we take the square root of the scalar product of the velocity with itself. So, we multiply and they take the product of the square root of the scalar product of this velocity into what the vector itself. So, this is what we are going to get. This gives you the absolute value of the velocity component in terms of the magnitude. So, the absolute magnitude of the velocity, which is supposed to be a vector, can be found out by expressing as the square root of the scalar product of the velocity multiplied with itself. So, this is the velocity multiplied by itself, and what we have defined the v velocity as, the v velocity is the relative velocity is 1 v1 or for the molecule corresponding to 1 and minus the velocity 2 corresponding to the molecules moving molecule 2 moving in the opposite direction. So, the expression can be expanded. You can produce the further extension of this by replacing what you have defined the v relative as. The v relative vector component is actually given as v1 minus v2, the vector components, and since it is multiplication you can write it this way, square it up, and if it is a square then you can see a minus b square formula, a square minus 2ab plus b square is how you are going to write that. So, if you are writing that, just have a look at it what we have written. Now, if we are going to find out the average of these terms, what we do? If we want to find out the average of these, we take the average of each of the velocities, and if you see in this term, since these are more or less random, so they are not correlated, they are random, not correlated, maybe orthogonal. So, if their vectors are orthogonal, their product is going to give you a 0. So, this term becomes 0. If this term becomes 0, then what we are left with, it is a square of the v1 and square of the v2 if we are taking the averages. So, this is the average v1 plus the average v square. So, the relative velocity what we have now come to is relative velocity, which can also be written as remember we either use v or c for the velocity component. Whenever we are writing a bar over it, it is meaning the mean or the average value, and this is how it is going to look, right. It is the square of v1 plus the square of v2 of the mean velocities. However, since the same velocity vectors would be associated with each of the molecules, because we are talking about most of the times we will try to simplify and take the molecules to be similar. So, they will be having the same type of same average velocity associated with them. So, each of them will be associated with the same type of velocity if they are of the same size or similar molecule, which we will always henceforth take that they are all similar kinds of molecules. So, if we do that, then you have this is a twice V1 square. So, if you take twice V1 square or V2 square, we just call it a V, that means the average speed. So, if it is average, they are all moving with the average speed V, then the relative mean velocity is nothing but under root into the mean velocity. What this mean velocity is what we had calculated from the kinetic model. What we are now getting, what is the mean velocity of approach of one molecule towards other. Okay. So, that is nothing but the relative velocity of approach is nothing but under root of the mean velocity calculated through the kinetic model. So, if you look at this, the relative mean speed or velocity, which we are usually relate with C rel, or we have a bar over that. This mean speed, which is one molecule approach with another, can be given as under root 2 into the mean speed. And if we substitute the value of C here, what is the value of C here? C is 8 pi r t by m pi to the power half. Okay. And you can replace this by r by kt, rt by kt, and mass by small mass. If you are, then you get the expression here like this. But remember, you have a different formula here. Here what we are talking about, this is not the molar mass which we are talking about in the kinetic model. Here this mass is the molecular mass. Okay, this is not the molar mass which was associated in the kinetic model, and this mass is the reduced mass of the two molecules which may be similar or dissimilar. Okay. So, what is this reduced mass given by? Reduced mass is nothing but the product of the mass, means what you take is 1 by Ma plus 1 by Mb. What is Ma and Mb are the two molecules. If you take 1 by Ma plus 1 by Mb is what you get is the reduced mass. You take the addition, if you add them two, what you get, it is Ma Mb divided by Ma Mb. Okay. So, the here we have replaced the we can simplify this to, if the molecules are identical, suppose that A and B are same molecules, then what does it become? Then you have the reduced mass becoming to half m. Okay. If it becomes half m, then you come back to the equation which you are dealing with. So, this becomes equal to m only when the molecules are of similar kind. Okay. So, you will be able to find out what is the relative velocity of approach for one molecule to the other. Only remember that here the denominator in the mass, in terms of, if you take it in terms of kT, this mass is not actually the mass of the substance, but it is the reduced mass of the substance which we are talking about. And here is m is the molecular mass which is associated with each of the molecule. Okay. Now, what happens when you are two molecules are approaching each other? Two molecules, when they are approaching each other with a relative speed, say a molecule has a diameter d, that is approaching another molecule, and in the volume which is going to sweep in interval t is let us say otherwise. Suppose I want to see which are the molecules which is going to be undergoing a collision. So, for understanding that, what we have to maintain a minimum distance from the centers of the two molecules. Now, for that, what we visualize is we take a volume which is going to be swept by a molecule of diameter d. When this is swept by a diameter molecule is sweeping a distance of some distance dt, and the volume it is going to cover is going to be a say tube, so or cylinder. So, this tube or cylinder which can be obtained is the volume in which within this whatever molecule is going to fall into will undergo collision. So, how I am going to define? I have to define a d molecule. See, d is this molecule, this is the diameter of the molecule. Now, it is going to sweep a volume and this volume is going to be associated with the sweeping of the total volume of at time t. So, if I have the we want to find out the total volume swept, what we have to look in time t interval is the tube with the radius d, this is the radius d, okay, and with the length of how much, when they are moving with the velocity, the molecules are moving with the velocity, the relative mean velocity of CRL, then when they are approaching this, what can we say? Then the volume which is going to sweep is going to be this is the length, okay, velocity equal to distance by time, okay. So, velocity into time is the distance, which we have done number of times. So, this is going to give you the length of the tube, and what is going to be the cross section? The cross section is going to be the diameter of the molecules. So, as we see, what we visualize is the number of collision that can be estimated from the number of gas molecules that have centers within this volume. Whichever molecules is having a center within this volume will undergo collision. Any other molecule which is not within this swept area will not be undergoing collision. Okay. So, a tube which we have swept using a molecule of diameter d is what is the volume in which the number of molecules included or number of molecules in this will undergo collision. So, to understand this more clearly, what we usually visualize that we have only one molecule which is moving, all other molecules in this swept area. Suppose you have a molecule D and it is going to sweep an area which is the molecules are moving with the velocity, relative means velocity of this, and this will sweep a volume of this. So, I see just visualize one molecule moving, all the rest of the molecules which have their centers within this tube are frozen. When they are moving, only one is going to move, and only those particles it is going to collide which is having the center within this tube. So, from if I know the total number of molecules in the tube, then I can find out how many collisions they are undergoing. Okay. So, if I know the number of collisions they are undergoing, that gives me the collision frequency. Okay. So, that is what we are going to see when a hit occurs, when the centers of two molecules come within the distance d with if they are similar kind of molecules, and this d is known as the collision diameter, and in order it is in the order of the actual diameter of the molecule. Now, the number z, the frequency can be given here, and we are going to just now derive how did we get this. How did we get this? Suppose the z is the number of collision made by one molecule in time interval delta t, which is during which the collision is counted. Then we multiply with the total number of molecules, the number density, then we can get the number of collision occurring per unit time. That will give us the frequency. So, number of collision made by one molecule per unit time into the number density will give you the total number of collision occurring in that area volume which we have swept. So, what is the number of collision? Number of collisions will be actually going to be the total number of molecules which will be occupying in the swept area. What is the swept area? This is the diameter pi, this is the area of cross section, where the diameter is supposed to be d square. So, pi d square is also known as sigma. Sigma is known as the collision cross section area into the distance. What was the distance? That was the velocity into time was giving you the distance of this length of this tube. So, this is the volume which is swept, swept by the molecule at unit time, that is dt, into the total number of molecule present, that is the number density, that is number of molecules per unit volume of the container. Okay. So, we can write down the number density in terms of NV, and if we look into this in a more detail, NV can be replaced by NV, number of molecules per unit volume can be replaced by in the number of moles into Avogadro number, gives you the total number of moles molecules divided by the total volume, and this total volume, since we are dealing with we can apply the ideal gas law, PV equal to nRT. So, we can find out what V is. V is going to be nRT by P. Okay. So, you replace nRT by P here, what you get? You get a expression in terms of the pressure. Okay. So, what we have, let us have a look at this, the collision frequency at constant volume. What is going to happen? At constant volume, collision frequency is going to increase with increase in temperature. See, the expression does not have a directly proportional temperature factor, but when we increase the collision frequency increases only when there is an increase in temperature if the volume is held constant. Why is this so? Because if you are increasing the speed, the relative mean speed of approach increases. So, since temperature increases the relative mean speed, because the relative mean speed has a term which is related to the speed. So, what we should remember is this expression of the frequency. In this expression we do not really have the temperature, but when you have a constant volume, when you have constant volume, increase in temperature will increase the relative speed, and hence the total collision frequency is supposed to increase. Now, what happens? We can also see that at constant temperature, the collision frequency is proportional to the pressure. Okay? If we are taking temperature as a constant, then the collision frequency is proportional to the pressure. Greater the pressure, greater the because what is going to be, how is pressure calculated? Pressure is the number of molecules which is exerting force on the walls. That is, if the number of particles are going to be increasing, that means the number density or number of particles is increasing, then the pressure is going to increase. So, pressure if you are having at constant temperature, temperature is held constant, the collision frequency is going to be increased if you increase the pressure, because if you are increasing the pressure indirectly means that you are increasing the number density of the gas particles, and if the number density increases, the pressure will increase, and that will, if number is increasing, they are more likely to collide. So, the frequency of collision will increase. So, the rate at which they encounter one another is going to be greater if you are increasing the pressure, and that means the number density, though their average speed remains the same, because we have held temperature constant. So, the average speed of approach remains the same, but the rate at which they encounter or strike each other, that means the collision frequency increases if you are increasing the pressure. Okay? Thank you.